Hello everyone, my name is Nguyen, and today on behalf of my research team, I will present about our paper titled Contrastive Viewpoint-aware Shape Learning for Long-Term Person Re-identification. Person re-ID is the task of matching persons across disjoint camera views in a multiple camera system. Given a query person, the aim is to re-identify that person by searching from a gallery of person images captured by the camera system. And this necessitates a deep learning model to learn the feature embeddings as person representations from the images for similarity matching. And in this work, we deal with long-term person re-ID, and different from traditional person re-ID, which deal with short-term scenarios. With long-term scenarios, we can see here, given the query image, the clothing of the person may have changed. The appearance is unobservable. Background, viewpoint, pose, illumination may have changed. So in short, long-term person re-ID pose several challenges, which are clothing change, viewpoint variations, pose variations, and occlusion. So generally, beyond appearance, we can capture body shape information for long-term person re-ID because body shape is more stable in long term. It can be unique across identities, and it can be invariant to clothing. And to capture body shape, we can use the skeleton-based pose. Skeleton is a graph of joints and bones, and each joint is a 2D point, which is the location of the joint in the image, and skeleton can be estimated by pose estimation models. However, viewpoint variations pose a lot of challenges for using skeleton-based pose. First, for example, with the side viewpoint, the skeleton is partially unobservable or occluded, which leads to ambiguous shape. And second, viewpoint changes lead to large intra-class gap and small inter-class gap in the latent space. For example, the same person A has highly dissimilar body shape under different viewpoint, which leads to far away feature embedding in the latent space. In contrast, the two different persons A and B under the same frontal viewpoint have similar shape, leading to close feature embeddings in the latent space. And the similar problem also happens to appearance. So, in order to deal with the first problem, we propose to use graph attention network that will operate on graph constructed from the skeleton. And graph attention network can help to learn discriminative shape representations across identities. And second, to minimize the intra-class gap and maximize the inter-class gap under viewpoint changes, we design contrastive viewpoint-aware loss functions to guide the model training. This is an overview of our proposed framework. Given a batch of images, we have the texture branch, which extract the appearance embeddings, and we also have the shape branch, which learn the shape embeddings. As a set of shape appearing embeddings and the appearance embeddings will be sampled for the proposed contrastive viewpoint-aware loss functions. And we will go into the details of the shape embedding branch later. Given the final appearance embedding and the shape embedding, they will be fused for the final person representation for similarity matching. For shape representation learning, it can be learned by capturing the local and the global relations among the skeleton joints. The diagram of the shape encoder is illustrated here. So given an image, first we use a pose estimator to obtain the joint set J, which consists of K body joints. Then the joints will be fed into the refinement network, which consists of several fully connected layers to capture the fine-grained details of each joint. Then the graph based on the skeleton will be constructed. Now each node is a feature embedding. Then we will use a graph attention network to capture the local and the global relations among the joints. And different from the traditional graph neural network, graph attention network implements an attention mechanism which can amplify the importance of each neighbor to a joint. This will be important when somebody passed, some joints are unobservable or occluded, then some other joints may contribute more to the shape embedding. And finally, the shape embedding will be obtained by global max pooling of the joint of the set of joints after the last attention layer. And to guide a model training for learning a latent space in which the shape and the appearance embeddings of the same person under different viewpoints are pulled closer and the different persons under the same viewpoint are pushed away, we design the contrastive viewpoint-aware losses. These losses are based on contrastive learning, in which we have given an anchor. Then the set of the positive images will be the images of the same identity, but under different viewpoints as visualized here. And the set of the negative images will be the images that of the different identity, but under the same viewpoint. So by minimizing this loss function, we can learn a latent space that serve our purpose. To evaluate the performance of our framework, we use two datasets, two long-term person reality datasets. First is LTCC, and second is PRCC, with some samples from the two datasets illustrated here. And we use two evaluation settings. First is clock changing, where only clock changing samples are used, and standard, where both clock changing and clock consistent samples are used. And we would like to note that the clock changing setting is more challenging. And two metrics, CMC scores of rank K or rank K accuracy and mean average precision are used for evaluation. These are the comparison in quantitative results between our framework and the current state of the art on two datasets. So overall, it can be seen that our framework outperforms the state of the art on both datasets in the clock changing setting. For example, we outperform Cal by 4.4% in rank 1 accuracy in clock changing and 3.2% in mean average precision. This demonstrates the effectiveness of our framework in real-world scenarios. In Ableton study, first we analyze the contribution of each branch to the overall framework, where we can see that texture still contributes more to the overall framework because texture remains more competitive when person do not change or only slightly change closest. And by coupling shape representation, we can see that we significantly improve reality accuracy under clocking change scenarios. And the effectiveness of the contrastive viewpoint-aware loss are also shown here, where by adding the contrastive viewpoint-aware loss, we can boost the reality accuracy in all model settings. And the proposed loss also show superiority over the traditional triplet loss. This is the visualize of the Disney distribution in the latent space of the embeddings, and we can see that the proposed loss function help to obtain a latent space in which the embeddings are more separable. And this is the end of our presentation. Thank you for listening.